Hey, welcome guys. So in this video, let's talk about a special polynomial ring. So previously we already talked about polynomial ring in the general field. So in this video, let's talk about a polynomial ring over rationals. Okay, so we will prove the two lemma. One is Gauss Lemma, one is the Einstein Criterion. So yes, the Einstein. So Einstein criterion. Okay, and the one is Gauss Lemma. Okay, so this is our main idea. Okay, so let f to be a polynomial with the coefficient or integers. So let's say a1 plus a1x up to the an xn, and all ai's are integer, are called primitive. This is called a primitive polynomial, called primitive if all the greatest common divisor is 1. Okay, so if all the coefficients are relatively prime, this is called a primitive. Okay, so lemma says that if f r g are primitive, then f and g is primitive. Okay, so maybe we just make a stupid example. So you see x squared plus 2 is primitive because their GCD is 1, right? So times x squared, let's say minus 2, right? You get x4 minus 4, right? So the coefficient GCD of 1 minus 4 is also 1, right? So any two primitive polynomial product will be primitive. Okay, so let's talk about a proof. Okay, so f is just, let's give a notation. And their GCD of A0 up to AN equals to GCD B0 up to Bn, which is 1. Okay, so what I'm saying is that suppose not. So suppose f times g are not primitive, it's not primitive. Okay, so that means there's something which is divisible by everything, right? Divisible by everything. So it is some prime p such that their products, right? So their product fg will be a0 b0 times a1 b0 a0 b1x, and keep going. And then there exists p such that all the coefficients are divisible by this p. So I want to prove that there will be contradiction, right? This is our goal. Okay. Okay, but I know that the f and g are primitive, right? So there must exist some b which is not divisible by p. Okay, so what I'm saying is that that aj to be the first coefficient of f of x, which p does not divide. Okay, and also the same thing that bk be the first coefficient that g of x, which p does not divide. Okay. So let's working on the cj plus k. So cj plus k is a coefficient of xj plus k. Okay, so obviously this is called aj bk plus aj plus 1, bk minus 1, aj plus 2, bk minus 2, aj plus k, b0, plus aj minus 1, bk plus 1, aj minus 2, bk plus 2, a0, bj plus k. Okay, by definition, this p must divide this, right? But the problem is that you see that p divides all of these things, right? Because aj is the first coefficient f of x. So p divides all of these. all of these things, right? Because AJ is the first coefficient that f of x which p does not divide. Okay. So by our choice also bk is the first coefficient that g of x which p net does not divide. So that means p divides what? So let's use another color. So p divides this. Because bk is the first coefficient that gx does not divide. So p divides all the number all the index less than k. So p divides this, p divides this, p divides this. Also in this one, p divides this, p divides this, p divides this. Okay, so p divides this and p divides this. So which tells you that p divides aj times bk. But the problem is that aj and bk does not p does not divide aj and both bk, right? And the p is prime. So this is contradiction. Okay, the reason is that if p divides aj and bk, since p is prime, so p must divide aj or p must divide bk, since p is prime. Okay, so there is a contradiction. Okay, so let's define the content. So the content of polynomial, contents of the p of f of x. So okay, given any integer coefficient polynomial, the content is defined to be a GCD of a0, a1 up to an. So the greatest common divisor of all the integer coefficients are called content. Okay. Let's see. Okay, so there's a lemma. Lemma says that if you times d to some polynomial, then your content is basically d times the polynomial of the content. So the proof is trivial, right? Because you times d of all these things, you can move out t. Okay. Okay, so theorem, Gauss Lemma. Okay, so Gauss Lemma says that if f is primitive, and it can be factored as a product of two polynomial. Suppose you get some primitive polynomial can be written as product of two polynomials with rational coefficient. So with the coefficient in rationals, then the f can be factored as a polynomial of the integers. Okay, so then f is a product of the two integers, integer polynomial. Okay, so this is a little bit hard to understand. So let me just write down the more explicitly. So what I'm saying is that if there exists h and g is in a rational coefficient, such that your f is h times g, then there will exist h tilde and g tilde, which are all the integer polynomial, such that f is h tilde g tilde. So this is called if f is primitive. Okay, so this is called Gauss Lemma. Okay, so the proof. So suppose you can write f is uv, where uv becomes a rational polynomial. You can clearing all the denominator. Taking all the common factors. So basically, you can write f as a belongs to b. Let's say lambda and so this is uv. So I use mu. I use m. Okay, so I can clearly put out all the rationals into a and divided by b and lambda m, such that lambda and m are basically the zx and the a, b are also integer. Okay. Okay. But I can clean all the coefficients, so I can make right. So I can make lambda and m, right? If lambda and n to be primitive. Okay, the reason is that if their content is not if its content is not 1, then I can just pull all the coefficient into a, right? So I can make all the coefficient of lambda m to be primitive. Okay, but by definition, since by our original lemma, right? If two primitive polynomial, their product must be primitive. So lambda m is primitive. So now you have one primitive function is a product of another primitive, right? So the only possibilities is that, right? So the content of this is 1. The content of this is 1, right? Okay, so which therefore that a must equals to b, and a divided by is 1. So f is just lambda mu. Okay. Yeah. Lambda m. Okay. Okay, just define. So I say an integer polynomial is called monic. Monic means that the highest coefficient of f is 1. So the highest coefficient is 1. Okay, so what I'm saying is that the f can be written as x to the power n and plus a minus 1, x minus 1, and keep going. Yeah, this is called a monic. So basically, the highest coefficient is 1. Okay, this is called monic. Okay, so we have the corollary. Okay, so let me just write down the corollary. The corollary says that if you have a monic polynomial, so if f is monic, and a factor into this product of two non-constant polynomial have rational coefficient, then it's factor as a product of two integer monic polynomial. So what I'm saying is that if f is monic and f is written as a gh, which is gs in q, there is a g tilde and the g tilde is z of x, d of x, and which so gs is non-constant. So f can be written as g tilde h tilde. Yeah, so this is leave as exercise. So by previous state that you can just use this lemma and yeah, make a change a little bit. Okay, so final theorem. I think the most important theorem in the rational field, the polynomial over rational field is called Einstein Criterion. Okay, so use let f to be this, and such that there exists the p prime p such that p let's say so p divides p do not divides an but p divides a1, p divides a2 up to p divides a0. So suppose that p there you can find such prime number it divides is not divides an but it do not divide an but it divides a0, a1, a2, and all the rest of a. And but p square. So my conclusion is p does not divide an, right? But p divides a0, but p squared do not divide a0. Okay. Then f of x is irreducible in Q. Okay, so that means you cannot write f as a gh such that the gs are all polynomial in x such that the degree g and the degree h are both greater or equal to 1. Okay, so the small corollary is that such f has no rational roots. Okay, so let's talk about examples. Right, so there are stupid example which is from high school is that x squared minus 2 has no real roots, right? Because you can take p equals to 2. Okay, which from here that 2 do not divide the largest one, right? But 2 divides this. 2 divides minus 2, but the 4, right? P squared 2 divides minus 2, but 4 do not divide minus 2. Okay, so for Einstein criterion, so one can use Einstein criterion to see that f is irreducible, right? Irreducible specific means that f is no rational root. Okay, so let me talk again. So you should find some p such that the p divides all the coefficient here, but p do not divide the final one, and the p squared do not divide the first one. Okay, then you can prove there's no such polynomial, and there's no f is irreducible. So you cannot write f into two products of rationals. Okay, so yeah, so so I can assume f is primitive, right? Because otherwise that I can pull out some coefficient. Okay. So p suppose we know that p does not divide a, right? So if f factors into polynomial, let's say g and h, so the highest power, right? So this f, the highest power is Sn, right? So highest power of g and h. Okay, so let's see. This is called BRXR. This is called the BCSXS, right? So I know that BRCS, right? So P do not divide. P do not divide PRCS. So which tell you that right? So this is the first condition. Okay, so maybe let me just write everything down. Okay, so to be easier. So suppose f is basically b0, b1x, brxr, and c0, c1x, csss. Okay, so I know the first coefficient. So a0 is b0, c0. Okay. So I know that p divides a0, right? So that means p either divides b0 or p divides c0. Okay. But I also know that yes, let me see. Oh shit. So yeah, so p squared do not divide a0, right? So so that means I have another condition is that p squared do not divide a0. Okay. Also, which tell you that there's only one possibility. Either p divides b0 or either p divides c0, right? Both you cannot happen. They cannot both happen. Okay, so from here that okay, so from here that let me suppose this is correct. I suppose p divides b0. Okay. Okay, the problem is that not all the so from here that not all the b's divides p. Okay, the reason is that if all of this divides p, if p divides b0 and then p divides b1 and up to p divides br, right? Then finally, then you will get the p. Then finally you will get what? Then you will get all f is divisible by p, right? If all of the contains p, then f is divisible by p. But I assume that f is primitive, right? So this cannot happen. So that means they cannot be all of these cannot divide by p, right? So let bk. So the same technique, let bk to be the first b such that such a coefficient b such that p do not divide bk. Okay, so this is so bk is the first one from left to right. That coefficient do not divide by b, do not divide by p. Okay. Okay, so from here that you know p divides bk minus 1. Okay. You know that ak, how about ak is bk c0, bk minus 1 c1, bk minus 2 c2, up to b0 ck. Okay. Okay, so from your definition, you know that p divides ak, right? P divides ak, right? By definition, p divides this, right? Let me just use a color. So by definition, p divides this, right? And the p divides what? P divides yeah, so p divides ak, right? But p divides this bk minus 1, right? But because any earlier it can be divisible by p, so it divides this, and divides all, right? But so the only thing needs to happen is that p divides bk c0, right? But p do not divide bk, which p must divide c0. Okay. But if p divides c0, which proves that the p squared should divide a0, right? But my assumption is that p squared cannot divide a0, so there is a contradiction. Okay, so this is why we cannot. Yeah, this is the proof. Okay, so you can construct a lot of examples. Let me just maybe construct another one. So remember that we need everything to be divisible by a0, right? But the p squared do not. So yeah, so right, so let's see. Suppose if I take f to be let's see. So we want the p to divide a0, right? So let's see. I use 3. So how about 9x? Let's say 15x squared plus let's say 4x cubed. Okay. So 3. So now 3 divides all the coefficient, right? Except for higher ones. So p divides all this. But 3 do not divide this, right? And the 9 do not divide the first one. Okay, so which tell you that the f is irreducible. Okay, so this is a powerful technique that in some case that you can easily distinguish which this is irreducible or not in a rational field. Okay, so see you guys in the next videos. Hope you guys subscribe to my channel. Bye bye.